The universe is home to oceans far beyond Earth, hidden seas beneath icy crusts, lakes of methane on alien moons, and even theoretical oceans of molten rock or metallic hydrogen. These mysterious bodies of liquid are more than just curiosities. They hold the keys to understanding the evolution of planets, the potential for extraterrestrial life, and the dynamic forces that shape the cosmos. Let's dive into the incredible variety of oceans scattered across our solar system and beyond. Europa's subsurface ocean, the search for life beneath the ice. Europa, Jupiter's biggest moon, is a planet of stark beauty and intriguing secrets. At first look, its ice surface appears bleak, like a frozen desert reflecting the little sunshine of the outer solar system. But under this frozen shell lies one of the most intriguing places in the quest for alien life, a massive subterranean ocean that is concealed and protected from the harsh vacuum of space. Europa's surface is a labyrinth of cracks, ridges, and chaotic terrain, a puzzle piece for scientists attempting to understand what lies below. The moon's crust, composed primarily of water ice, is estimated to be tens of kilometers thick. But the evidence for a global ocean beneath this frozen shell is compelling. Observations from spacecraft like Galileo and Hubble have revealed the presence of a thin atmosphere composed of oxygen, likely formed by the interaction of Jupiter's radiation with Europa's icy surface. This process releases water vapor, a clue pointing toward the existence of liquid water below. The surface itself tells a story of dynamic activity. Europa's chaotic terrain, with its fractured ice plates and ridges, is thought to be caused by the movement of liquid water or slushy ice from the subsurface ocean. These features resemble processes seen on Earth, such as the upwelling of material beneath glaciers, suggesting a dynamic interaction between the ice and the liquid layer below. In some regions, reddish-brown streaks crisscross the surface, likely caused by salt or other materials deposited by water seeping up through cracks. These deposits may even contain organic compounds, adding to Europa's intrigue. But how does liquid water persist beneath such a thick layer of ice in the frigid outer reaches of the solar system? The answer lies in tidal heating. Europa's orbit around Jupiter is slightly elliptical, causing the Moon to experience varying gravitational forces as it moves closer to and farther from the gas giant. This constant gravitational tug warps Europa's shape, creating friction and generating heat within its interior. This heat prevents the subsurface ocean from freezing entirely, maintaining a liquid state despite surface temperatures that plunge to minus 160 degrees Celsius, minus 260 degrees Fahrenheit. Models suggest that this ocean could be as deep as 100 kilometers, holding more water than all of Earth's oceans combined. The implications of such an environment are profound. On Earth, wherever we find liquid water, we find life. Could the same be true for Europa? The ocean beneath its icy shell might contain the essential ingredients for life as we know it: water, energy, and nutrients. Hydrothermal vents on Europa's ocean floor, powered by tidal heating, could mimic the deep-sea vents on Earth, where life thrives in total darkness. These vents could provide a steady source of heat and chemicals, fostering microbial ecosystems, or even more complex organisms. The goal of future tasks is to find out what's going on. When NASA's Europa Clipper launches in a few years, it will do close flybys of Europa and look at its surface and atmosphere for signs of life. The satellite will have high-tech tools on board that can find plumes of water vapor, measure the makeup of the surface, and make a map of the ice shell's thickness. If plumes are present, they might give a clear view into the ocean below, letting scientists study its chemicals without having to drill through the ice. Enceladus's water plumes, a gateway to its hidden ocean. The beautiful water droplets on Enceladus, a small moon of Saturn, have caught the attention of both experts and space fans. NASA's Cassini probe found these plumes for the first time in 2005. They come from the south pole of Enceladus and spray water vapor, ice particles, and organic molecules into space. They give us a clear view of the ocean below the moon's icy surface, which makes Enceladus one of the most interesting places to look for life beyond Earth. The plumes are believed to originate from fractures in Enceladus's ice crust, known as tiger stripes. These long, linear fissures allow material from the subsurface ocean to escape into space, driven by pressure and thermal activity. The discovery of these jets transformed Enceladus from an unassuming icy moon into a prime target for astrobiology. Not only do the plumes reveal the existence of a liquid ocean, but they also suggest that this ocean is in direct contact with the moon's rocky core, enabling complex chemical interactions. Cassini's flybys through the plumes provided detailed insights into their composition. The spacecraft detected water vapor, carbon dioxide, methane, and organic compounds, including simple hydrocarbons. Even more compelling was the discovery of molecular hydrogen, H2, which is a key indicator of hydrothermal activity. On Earth, hydrothermal vents at the ocean floor are home to rich ecosystems, fueled by chemical reactions between water and rocks. The presence of molecular hydrogen on Enceladus suggests that similar reactions may be occurring, providing a potential energy source for microbial life. The presence of hydrothermal activity implies that Enceladus's ocean floor is geologically active. This activity is driven by tidal heating, similar to Europa. As Enceladus orbits Saturn, gravitational interactions with the planet and neighboring moons create friction within its interior, generating heat. This heat keeps the subsurface ocean in a liquid state and powers the hydrothermal processes that sustain the plumes. What this means for life on Enceladus is very important. Under the moon's icy surface, there is a place that might be livable because of flowing water, organic molecules, and chemical energy. On Earth, life does well in similar conditions, even when there is no sunshine. Microorganisms that live near volcanic vents get their energy from chemosynthesis, a process that uses chemical reactions instead of sunlight. Enceladus might have a similar kind of life that feeds on the molecular hydrogen and other substances made by the moon's hydrothermal processes. Enceladus's plumes also make it uniquely accessible for scientific study. Unlike Europa, whose ocean is buried beneath kilometers of ice, Enceladus's plumes provide direct samples of its subsurface ocean. Future missions could fly through these jets to collect material for analysis, offering a relatively straightforward way to study the moon's habitability. Instruments could search for more complex organic molecules or even biosignatures, chemical indicators of life. The Enceladus Life Finder, ELF project, is one that wants to do that. ELF would fly through the clouds and look for signs of biological activity in the stuff that was thrown up. The Enceladus Orbilander is a different idea that mixes orbital studies with a lander to get a much better look at the moon's surface and plumes. These kinds of projects could change the way we think about icy moons and their ability to support life. Titan's methane seas, the only known liquid lakes beyond Earth. Among Saturn's moons, Titan is the largest. In the solar system, it is somewhat special. Benevolent large lakes and seas of liquid methane and ethane lie under its hazy, thin layer. Only known consistent bodies of liquid found on a celestial planet other than Earth are these ones. Titan's methane seas are an unusual and fascinating environment that can help us understand other liquid systems and the prospect of unusual life forms surviving in quite different conditions than those on Earth. Unlike Earth's water-based hydrological cycle, Titan's landscape is shaped by a hydrocarbon cycle. Methane and ethane, hydrocarbons that are gases at Earth's surface temperatures, exist as liquids on Titan due to its frigid surface temperature of around -179 degrees Celsius, -290 degrees Fahrenheit. This cycle mirrors Earth's water cycle, with liquid methane and ethane evaporating, forming clouds, and precipitating back to the surface as rain. This creates dynamic weather patterns that carve rivers, fill lakes, and sculpt Titan's terrain. The largest known methane sea on Titan is Kraken Mare, which spans hundreds of kilometers. Nearby are other massive bodies of liquid, such as Ligeia Mare and Punga Mare. These seas are surrounded by smaller lakes, rivers, and drainage channels, suggesting an active and evolving surface. Observations from NASA's Cassini mission revealed that these seas are incredibly deep, with Kraken Mare plunging to depths of over 300 meters in some areas. The composition of these bodies is primarily methane, with varying concentrations of ethane and dissolved nitrogen. The makeup of Titan's lakes is one of the most interesting things about her. At Titan's very cold temperatures, methane acts like water does on Earth. This creates the possibility of a new kind of prebiotic chemistry in which complex organic molecules could grow and gather. Cassini's measurements also found acetylene, hydrogen cyanide, and other organic molecules on and in Titan's atmosphere. These are the building blocks of more complex organic systems. A lot of people have different ideas about whether or not there could be life in Titan's methane seas. Life as we know it needs water that is liquid, but could it change to use methane instead? Some scientists think that possible living things on Titan might be able to use liquid methane as a solvent and have biology that is very different from our own. For example, these living things could break down hydrogen and acetylene, making methane a waste. This is the opposite of how life works on Earth, where life is based on water. Titan's atmosphere plays a crucial role in its methane cycle and surface chemistry. Composed primarily of nitrogen, with small amounts of methane and other trace gases, the atmosphere is dense and dynamic. Methane clouds form and move across the Moon, producing localized rainstorms that refill its lakes and rivers. The thick haze, created by photochemical reactions in the upper atmosphere, scatters sunlight and limits visibility, adding to Titan's otherworldly ambience. Future exploration of Titan aims to unravel these mysteries. NASA's upcoming Dragonfly mission, set to launch in the mid-2020s, will deploy a rotorcraft to explore Titan's surface and atmosphere. Dragonfly will investigate the chemistry of Titan's dunes and lakes, searching for complex organic molecules and assessing the Moon's potential for life. With its ability to hop between locations, Dragonfly will provide unparalleled insights into Titan's surface processes and chemical diversity. Titan's methane oceans throw doubt on our knowledge of habitability and increase the range of options for what may be a liquid world. Studying this alien moon will let scientists investigate the boundaries of chemistry, the possibility for life outside Earth, and the intriguing dynamics of a hydrocarbon-dominated environment. Ganymede's deep ocean layers, a stacked world of water and ice. Ganymede, the solar system's biggest moon and Jupiter's partner, is a harsh environment. A large underground ocean exists underneath its frozen cover, which may be coated with water and ice in a stacked arrangement. Ganymede's distinctive structure makes it an intriguing subject for planetary scientists and astrobiologists alike, since it may provide hints about how such moons form and their potential for habitability. One of Ganymede's most notable aspects is its intricate interior structure. Unlike Europa, where the ocean is expected to be in direct touch with the rocky mantle, Ganymede's water is thought to be sandwiched between numerous layers of ice. This layered ocean concept describes a high-pressure environment with liquid water sandwiched by ice phases of different density. The top layer is solid ice, but underneath it, the interaction of heat and pressure produces liquid water zones and high-pressure ice forms like Ice 6 and Ice 7. Evidence for Ganymede's ocean comes from its magnetic field. Observations by the Galileo spacecraft revealed that Ganymede generates its own magnetic field, a rarity among moons. This magnetic field interacts with Jupiter's powerful magnetosphere, creating unique auroras. The slight wobble in these auroras, observed by scientists, indicates the presence of a conducting layer beneath Ganymede's surface, a layer most likely composed of salty liquid water. Ganymede's ocean is shaped in large part by the tremendous pressure within its core. The surface temperature of Ganymede can drop to minus 200 degrees Celsius, minus 328 degrees Fahrenheit, freezing the outermost layers. However, tidal forces from Jupiter, as well as residual heat from Ganymede's creation, supply sufficient warmth to keep liquid water beneath the ice. The pressure from the Moon's upper layers compresses the water, leading it to behave differently than on Earth, with certain areas perhaps producing supercooled slush rather than liquid. Another interesting thing is the makeup of Ganymede's water. The Moon's icy top might have elements like magnesium sulfate in it, but the ocean below the surface is probably full of salts, that make it better at conducting electricity. This saltiness shows that the ocean and the hard basement below are interacting, making a geochemical environment that might be able to support life. Deep-sea hydrothermal vents on Earth are home to communities that are growing because of similar processes. Ganymede's surface also provides clues about the dynamics of its ocean. The Moon is covered in a mix of bright and dark terrain, with the brighter regions showing signs of tectonic activity. Grooves and ridges crisscross its surface, hinting at past episodes of crustal movement that may have been influenced by the subsurface ocean. This activity suggests that Ganymede's ocean may not be static, but instead undergoes periodic changes, such as freezing and thawing cycles or shifts in its ice layers. While Ganymede's ocean may be less accessible than those on Europa or Enceladus, it still represents a compelling target for future exploration. NASA's upcoming Europa Clipper mission will also conduct flybys of Ganymede, using its instruments to gather data on the Moon's surface composition and magnetic field. Additionally, the European Space Agency's Jupiter Icy Moons Explorer, JUICE, will focus extensively on Ganymede, aiming to map its ice shell and study the interaction between its surface, ocean, and magnetosphere. The finding and study of Ganymede's stacked ocean system shows that the solar system has a lot of different kinds of icy worlds. Ganymede is a great place to study how moons are formed and whether they could support life because it has a unique mix of ice, liquid water, and movements caused by pressure. Callisto's frozen secrets, an ocean locked beneath ancient ice. Callisto, the second largest moon of Jupiter, is often overshadowed by its more famous neighbors, Europa and Ganymede. However, this ancient, heavily cratered moon holds its own mysteries, including the possibility of a hidden ocean beneath its thick ice shell. Unlike Europa or Ganymede, Callisto has remained geologically inactive for billions of years, preserving its surface as a time capsule of the early solar system, while potentially harboring a liquid ocean deep below. The first hints of Callisto's subsurface ocean came from observations by NASA's Galileo spacecraft. The spacecraft detected variations in Callisto's magnetic field, similar to those observed on Ganymede. These variations suggest the presence of a conductive layer beneath the surface, likely a salty ocean. Unlike Europa, where the ocean interacts more dynamically with the icy crust, Callisto's ocean lies buried under a much thicker layer of ice, estimated to be several hundred kilometers thick. The surface of Callisto is very different from the surfaces of Europa and Ganymede, which are younger and more active. It is one of the things in the solar system with the most craters, and its shape hasn't changed in billions of years. Callisto is a great place to learn about the early solar system, because it hasn't been affected by physical action in a long time. On top, there is a mix of ice and rock, and big areas like Valhalla and Asgard show the marks of huge strikes. These areas make it seem like Callisto's crust might be broken, giving us hints about the planet's structure and the possibility of an ocean below the surface. Unlike Europa and Ganymede, which are actively heated by tidal forces from Jupiter, Callisto is located further from the giant planet, experiencing much weaker gravitational interactions. As a result, Callisto's interior is colder and less dynamic. Any liquid ocean beneath its crust is likely sustained by residual heat from the Moon's formation and the insulating properties of its thick ice shell. This ocean, if it exists, would be more isolated than those on Europa or Enceladus, raising questions about its chemical composition and potential for habitability. Astrobiologists may still be interested in Callisto's ocean below, even though it doesn't seem to be doing anything. Since the ocean is by itself, it might go through strange chemistry changes, especially if the water mixes with minerals in the core's rocks. It's possible for microbes to live in liquid water, even if there is no clear proof of hydrothermal activity. This is true even in very harsh circumstances. Callisto's ancient surface and possible ocean also make it an appealing target for future exploration. The Moon's lack of significant geological activity means that its surface is relatively stable, making it a safer landing site compared to the more volatile Europa or Io. NASA's proposed concepts for missions to Callisto include orbiters and landers designed to study its surface and internal structure in detail. These missions could use radar to probe the ice and determined the depth and extent of the subsurface ocean. The frozen secrets of Callisto teach us that even the most remote worlds can hide deep secrets. Its thick ice shell and buried ocean make it a very different kind of setting from the ones nearby that are more busy. Scientists can learn more about the different kinds of icy moons and the different kinds of conditions that underground seas might form and stay in place by studying Callisto. Rhea's ice shells, evidence of a hidden ocean. Rhea, Saturn's second largest moon, is often forgotten when people talk about oceans. But new research suggests that below its highly cratered surface lies a secret body of water that is protected by a thick layer of ice. Even though Rhea isn't as active as Europa or Enceladus, its unique features make it an interesting place to study the variety of oceans below the surface of the solar system. The evidence for a hidden ocean on Rhea comes from its low-density composition and gravitational anomalies detected by the Cassini spacecraft. Rhea's density suggests a mix of rock and ice, but variations in its gravitational field indicate the possibility of a differentiated interior. This means that Rhea's core and outer shell might be separated by a layer of liquid water, maintained by heat, generated from the decay of radioactive elements in its rocky core. Rhea's crust is quite stable and undisturbed, unlike the dynamic plumes of Enceladus or the surface characteristics of Europa. This stability implies that functioning as an insulating layer preserving the beneath liquid water across geological timeframes, its ice shell might be thicker than that of its counterparts. The lack of notable tectonic activity on Rhea also suggests that, should it exist, its ocean is more isolated, thereby possibly generating special chemical conditions. The composition of Rhea's potential ocean is another area of interest. While Europa and Enceladus are believed to host salty oceans, Rhea's liquid layer might be less saline or even rich in ammonia, which acts as an antifreeze and allows water to remain liquid at lower temperatures. Such an environment would present unique challenges and opportunities for life, requiring organisms to adapt to low temperatures and limited energy sources. Rhea's lack of surface activity makes discovering a subsurface ocean challenging. Future missions, equipped with upgraded radar and gravity-measuring instruments, may provide more definitive evidence. These technologies may detect variations in the thickness of Rhea's ice cover, or identify locations where liquid water interacts with the rocky core. Ceres' salty brine pockets. Oceans on a dwarf planet. Ceres, which is the biggest object in the asteroid belt, might not seem like a good place for oceans to exist. However, data from NASA's Dawn probe showed interesting signs of liquid reserves hidden beneath its icy surface. These areas of salty brine that have been kept inside the dwarf planet give us a rare look at what it might be like for small icy worlds to have liquid water. The strongest evidence for brines on Ceres comes from observations of bright spots on its surface, most notably in Okator crater. These bright regions are composed of sodium carbonate and other salts, which are typically associated with liquid water. Scientists believe that these salts were carried to the surface by liquid brines that seeped up through fractures in the crust, where they froze and crystallized. Ceres' relatively small size makes the presence of liquid water surprising. Without strong tidal heating or significant geothermal activity, it was long assumed that Ceres' interior would be completely frozen. However, the salts in its crust act as natural antifreeze, lowering the freezing point of water and allowing brines to persist in localized pockets. These brines might be remnants of a larger subsurface ocean that has mostly frozen over time. The chemical composition of Ceres brines also provides clues about the dwarf planet's history. The high concentration of sodium carbonate suggests prolonged interactions between water and rock, a process that could release essential nutrients into the liquid reservoirs. If microbial life ever existed on Ceres, these brines might represent its last refuges. Ceres doesn't have as much surface activity as moons like Enceladus, but it does sometimes show signs of cryovolcanism. The dome-shaped Ahunamons on Ceres' surface is thought to be a cryovolcano that exploded with a mix of water, ice, and salts. This kind of action suggests that liquid reserves under Ceres' crust can sometimes interact with the surface, giving us a look into what's inside. Tethys' hypothetical ocean. A moon frozen in time. Tethys, one of Saturn's mid-sized moons, appears at first glance to be an unremarkable icy world. Its surface is heavily cratered, with minimal evidence of geological activity. Yet some scientists believe that beneath its frozen exterior, Tethys may harbor a subsurface ocean, making it a potential candidate for further exploration in the search for alien oceans. Evidence for a hypothetical ocean on Tethys comes from its unique surface features and internal structure. One of the most striking landmarks on the Moon is Ithaca Chasma, a massive canyon system that stretches across nearly 3/4 of Tethys' circumference. This chasm is thought to have formed during an early period of the Moon's history, when its internal ocean began to freeze, causing the ice shell to expand and crack. These surface deformations hint at a dynamic interior, one that may have supported liquid water in the past, or might still do so today. Tethys' low density, composed primarily of water ice with small amounts of rock, further supports the possibility of a liquid layer beneath its surface, while the Moon's relatively small size and distance from Saturn suggest limited internal heating. Tidal interactions with the planet and its neighboring moons may provide enough energy to maintain a thin subsurface ocean. Such interactions are well documented on other moons, like Enceladus, where tidal forces drive active geysers. If Tethys does harbor a subsurface ocean, its chemistry would likely be distinct from that of other ocean-bearing moons. The relatively low levels of surface activity suggest a more stable environment, where salts and other compounds might accumulate over time. This unique chemistry could create conditions for long-term habitability, albeit on a microscopic scale. The challenges of detecting an ocean on Tethys stem from its lack of obvious surface activity, such as the plumes seen on Enceladus or the ridges on Europa. However, future missions equipped with radar systems capable of penetrating ice shells could provide more definitive evidence. Gravity mapping and thermal imaging might also reveal subtle anomalies indicative of liquid reservoirs beneath the surface. Mars' ancient oceans. Where did all the water go? Mars used to have a lot of water, but now it's just a cold, empty desert. On its surface, natural features like valleys, deltas, and shorelines show signs of seas, lakes, and rivers that were there in the past. There may have been a huge ocean in the north of Mars billions of years ago that covered almost a third of the world. This ocean may have been there for a long time enough to make conditions good for microbes. Its disappearance is one of the biggest puzzles in the study of planets. The evidence for Mars's ancient oceans comes from multiple sources. Orbital images reveal features like dried-up riverbeds and outflow channels, which suggest that large volumes of water once flowed across the surface. Additionally, sedimentary deposits in regions like Gale Crater and Jezero Crater indicate the presence of long-standing lakes. Some of these deposits even show layered structures, similar to those formed in terrestrial deltas and shorelines. The existence of what seem to be shorelines in Mars's northern hemisphere is among the most convincing evidence of an ancient ocean. These characteristics, which abound in areas like Arabia Terra and Vastitas Borealis, point to the low-lying northern plains of the planet previously having a great body of water. This theory is supported by models of Mars's early past, which suggest that the planet most certainly had a thicker atmosphere able to preserve liquid water on its surface. There are many parts to the story of why Mars water disappeared. A lot of it was probably lost to space because the planet's atmosphere was getting thinner. Mars doesn't have a world magnetic field like Earth does to protect its atmosphere from the solar wind. Over time, this slowly removed the gases in the atmosphere, lowering the surface pressure and making it impossible for water to be liquid. According to data from NASA's MAVEN, Mars Atmosphere and Volatile Evolution Project, air escape was a big part of how Mars changed. Some of Mars's water may still be hidden beneath its surface. Radar data from missions like Mars Express and the Mars Reconnaissance Orbiter have detected subsurface ice deposits at mid-latitudes and polar regions. These reserves could represent the remnants of ancient oceans, now frozen in the planet's crust. There is also speculation that liquid water might persist underground in isolated pockets, heated by residual geothermal activity. The loss of Mars's oceans had huge effects on its ability to support life. In the past, when Mars was warmer and wetter, it may have been a thriving world where microbes could have lived. Clay minerals and sulfates found in old rocks from Mars show that the planet's water used to be neutral to slightly alkaline, like the water in Earth's seas. These results give us more faith that signs of past life may still be kept in the Earth's rocks and layers below the surface. The goal of future trips is to find out more about Mars's past oceans. As it explores Jezero crater, NASA's Perseverance rover looks for signs of microbes that lived in what used to be a lakebed. The Rosalind Franklin rover from the European Space Agency will also look for organic chemicals and biosignatures below the surface. Together, these projects and ongoing research from orbiters and landers help us learn more about what happens to Mars's water and what that means for the planet's habitability. Earth's twin, no more. Venus's lost oceans. Venus, often called Earth's twin due to its similar size and proximity, has a vastly different environment today, an inferno with surface temperatures exceeding 470 degrees Celsius, 880 degrees Fahrenheit, and crushing atmospheric pressure. However, Venus wasn't always the uninhabitable world we see today. Evidence suggests that it once had shallow oceans and a more temperate climate billions of years ago. The loss of these oceans and the subsequent transformation into a hellish landscape offer crucial lessons about planetary evolution and climate change. The idea that Venus once had liquid water stems from studies of its atmosphere and surface. Measurements from spacecraft like NASA's Pioneer Venus and the European Space Agency's Venus Express revealed an unusually high ratio of deuterium to hydrogen in Venus's atmosphere. Deuterium, a heavier isotope of hydrogen, is left behind when lighter hydrogen escapes into space. This suggests that Venus had large quantities of water in the past, much of which was lost over time. The surface of the world also shows that it was wet in the past. NASA's Magellan project used radar to map out huge areas that may have been formed by ancient water flows or shallow seas. Like Earth's continents, Venus's high continents, like Ishtar Terra and Aphrodite Terra, could be places that used to be above these made-up seas. The transformation of Venus from a potentially habitable world to its current state was driven by a runaway greenhouse effect. Billions of years ago, Venus may have had a temperate climate with liquid water on its surface. However, increasing solar radiation from the young sun likely caused more water to evaporate into the atmosphere. Water vapor is a powerful greenhouse gas, and its accumulation would have amplified the warming process, causing even more water to evaporate. This positive feedback loop eventually led to the complete evaporation of Venus's oceans. Venus no longer has oceans to keep its temperature stable and store carbon dioxide, so CO2 has taken over its atmosphere. The thick atmosphere held heat, which raised the temperature of the surface to unbearable levels and stopped any flowing water from returning. More greenhouse gases were released into the atmosphere by volcanic activity, which probably made things worse by making the heat even worse. The geology and temperature of Venus suffered greatly by the disappearance of her seas. The surface of the planet today is covered in shield volcanoes and volcanic plains. There is no evidence of plate tectonics as on Earth. Venus's crust became stationary without water to lubricate tectonic processes, storing heat and leading to regular worldwide resurfacing. Venus's early history may have been destroyed by this resurfacing. Hence, the precise chronology of her metamorphosis is unknown. Venus's destiny reminds Earth and other possibly livable worlds of a lesson. It emphasizes the fine equilibrium needed to preserve liquid water and a steady temperature. Researching Venus's past can help one get an important understanding of the elements influencing a planet's habitability, as well as possible weaknesses of Earth's climate system. Future Venus missions are designed to uncover additional information regarding its aquatic past. The Da Vinci Plus and Veritas projects from NASA and Envision from ESA will look at Venus's atmosphere, surface, and geological past in a way that has never been done before. These projects will look for signs about how the Earth's climate changed in the past and how its oceans disappeared. By comparing Venus to Earth, scientists hope to learn more about the range of potential outcomes for Earth-like worlds in the habitable zone. The missing oceans of Proxima Centauri b. Proxima Centauri b, a rocky exoplanet orbiting the closest star to our solar system, has captured the attention of astronomers since its discovery in 2016. Located just 4.2 light-years away, it lies within the habitable zone of its star, where conditions might allow liquid water to exist. However, whether Proxima Centauri b hosts oceans beneath its surface remains an open question, one that holds profound implications for the search for life beyond Earth. Proxima Centauri b orbits its red dwarf star at a distance of only 0.05 AU, about 20 times closer than Earth is to the Sun. Despite this proximity, the planet receives a similar amount of energy due to the dimness of its star. This positioning places it within the habitable zone, where temperatures might permit liquid water. Yet proximity to a red dwarf also comes with challenges, particularly the intense stellar flares and radiation emitted by these stars, which could strip away a planet's atmosphere and surface water over time. The presence of oceans on Proxima Centauri b depends heavily on the planet's ability to retain its atmosphere. If it has a strong magnetic field, it could shield the atmosphere from the star's radiation, preserving conditions suitable for liquid water. Without such protection, the atmosphere could have been eroded early in the planet's history, leaving it barren and dry. Proxima Centauri b is probably tidally locked, in which case one side always faces the star while the other stays permanently dark. Extreme temperature disparities resulting from this between the two hemispheres might affect water delivery. Should oceans exist, they may be concentrated in a terminator zone, that which is between the day and night sides, or create large ice sheets on the dark side, while liquid water pools on the sunny side. Studies of Proxima Centauri b's composition also help to guide speculation about its seas. Proxima Centauri b, a rocky planet with an estimated mass at least 1.2 times that of Earth, might have kept water during its development, particularly if it started as an ice body moving inward. Alternatively, as Earth's instance shows, water might have arrived from cometary collisions. Without actual observations, these situations remain speculative. Red dwarf stars, like Proxima Centauri, are known for having strong stellar flares that happen often. Flares like these send out bursts of high-energy radiation that can remove atmospheres and water from the surface of planets. A big worry for Proxima Centauri b is that these flares might make it impossible for life to exist there. If the world could build up a thick atmosphere full of greenhouse gases like carbon dioxide, it might keep temperatures from getting too high or too low, and keep any oceans from drying up. In this case, Proxima Centauri b might look like an earlier Earth that was warmer and wetter, or even Venus. Exoplanet atmospheres will be studied in more depth than ever before with instruments like the James Webb Space Telescope, JWST, and new sites like the Extremely Large Telescope, ELT, and the Habitable Worlds Observatory. Scientists want to find water vapor, oxygen, or other biosignatures that could mean there are oceans or life on other planets by looking at light going through the planet's atmosphere during transits. In addition to studying the atmosphere, direct imaging may also be used to look for Proxima Centauri b's seas. One day, high-tech methods like starshade technology might be able to block out Proxima Centauri's light, letting cameras take pictures of the planet itself. Surface traits like glinting rays could be direct proof of water that is liquid. The star Proxima Centauri b is a tempting chance to learn more about the possibility of foreign seas and life just beyond our solar system. It is close to Earth and in the livable zone, which makes it a great place to explore. Kepler 22 b, an ocean world in the habitable zone. Discovered by NASA's Kepler spacecraft in 2009, Kepler-22b is an exoplanet among the most fascinating prospects for having alien seas. This super-Earth, which lies 620 light-years in the constellation Cygnus, is in the habitable zone of its parent star, where circumstances would permit liquid water to exist. Although much about Kepler-22b is yet hypothetical, its size, position, and possibility to be a water-rich planet draw attention in research of far-off worlds. Kepler-22b orbits a star similar to our Sun, classified as a G-type main sequence star. The planet's orbital period is 290 days, placing it comfortably within its star's habitable zone. This zone is defined as the region where the amount of stellar radiation is just right to maintain liquid water on the surface, assuming an Earth-like atmosphere. The energy received by Kepler-22b is estimated to be about 25% less than Earth receives from the Sun, suggesting a slightly cooler environment that could still sustain oceans, especially if greenhouse gases are present to trap heat. The size of Kepler-22b is one of the things that makes it unique. It is a super-Earth because its radius is about 2.4 times that of Earth. A super-Earth is a planet that is bigger than Earth, but smaller than an ice giant like Neptune. This range of sizes is important because it makes it more likely that the planet will have a thick atmosphere and enough gravity to hold water. However, no one knows for sure what it is made of. Kepler-22b could be made of rocks, ice, or a mix of the two. Its atmosphere is likely thick, which could hide a liquid surface. The idea that Kepler-22b might be an ocean world comes from models of how it is put together. People often think that deep seas cover the whole area of super-Earths in the habitable zone. If Kepler-22b has a thick atmosphere full of water vapor, it could have oceans that are hundreds of kilometers deep. Even though it wouldn't have any countries or land masses like Earth does, it could still have life that is adapted to living in water. Another consideration is the planet's potential atmospheric composition. If Kepler-22b has a substantial atmosphere with greenhouse gases like carbon dioxide or methane, it could maintain surface temperatures warm enough for liquid water. Alternatively, if the atmosphere is dominated by hydrogen and helium, the planet might resemble a mini Neptune, with a thick gaseous envelope overlying a dense core and high-pressure water layers. This would make it less likely to support surface oceans, but still intriguing for its unique chemistry. The habitability of Kepler-22b also depends on its internal heat and geological activity. If the planet has a molten core, geothermal energy could drive processes like volcanism and plate tectonics, which play crucial roles in recycling nutrients and supporting ecosystems on Earth. In an ocean-covered world, such activity could create hydrothermal vents on the seafloor, providing a potential energy source for life. On Earth, similar environments host thriving communities of organisms, even in the absence of sunlight. A difficulty in researching Kepler-22b is the dearth of direct observational data. The surface and atmosphere of the planet cannot be precisely resolved by current telescopes, so much remains to be theoretically modeled and indirectly supported. Future projects such as the James Webb Space Telescope, JWST, and other ground-based telescopes seek to examine the atmospheres of exoplanets including Kepler-22b. Scientists can hunt for water vapor, carbon dioxide, or other indicators of ocean existence by examining the light filtered through the planet's atmosphere during transits. While the specifics of Kepler-22b's environment remain uncertain, its potential to host an alien ocean sparks significant interest. If confirmed, it would provide a valuable comparison to Earth and expand our understanding of the diversity of habitable worlds in the universe. Whether it is a global water world or a more complex environment, Kepler-22b underscores the vast possibilities for life-sustaining planets beyond our solar system. Oceanic evidence on early Earth, the Archean era. From around 4 billion to 2.5 billion years ago, the Archean era is among the most transforming times in Earth's past. Earth's seas were very different from what we know now during this period. Less oxygenated, richer in dissolved iron, and impacted by a youthful, volatile atmosphere. Early biosphere and the evolution of life as we know it were greatly shaped by these primordial waters. Archean oceans were dominated by chemical conditions that were largely anoxic, meaning they contained little to no oxygen. Instead, they were rich in dissolved iron, which gave them a distinct greenish tint. This iron came from volcanic activity and hydrothermal vents, which released minerals into the water. The abundance of dissolved iron set the stage for the formation of banded iron formations, BIFs, sedimentary rocks that record the interplay between iron and oxygen-producing organisms. The Archean atmosphere was also vastly different, with high levels of methane and carbon dioxide, creating a greenhouse effect that kept the oceans from freezing despite the sun being significantly dimmer than it is today. This phenomenon, known as the faint young sun paradox, highlights the importance of atmospheric composition in regulating early Earth's climate and sustaining its oceans. Life in the Archean oceans was limited to microbes, primarily anaerobic organisms that thrived in oxygen-poor environments. Among these were the first photosynthetic bacteria, such as cyanobacteria, which use sunlight to convert carbon dioxide and water into organic compounds. This process also released oxygen as a byproduct, slowly altering the chemistry of the oceans and the atmosphere in what is now known as the Great Oxidation Event, which occurred after the Archean era. Hydrothermal vents in the Archean oceans likely served as hotspots for early life. These vents provided not only heat, but also a rich supply of nutrients and minerals that supported microbial ecosystems. The discovery of similar ecosystems in Earth's modern oceans suggests that such environments could have been critical to the origin of life. The chemical gradients around these vents offered a natural laboratory for the development of primitive metabolic pathways and complex organic molecules. Geological proof for the Archean oceans comes from old rock forms like stromatolites, which are stacked structures made by microbial mats. These fossils show us what kinds of animals used to live and grow in the deep seas. Scientists can figure out what the Archean oceans were like and learn more about early life by studying these structures. The Archean era is studied because it shows how the oceans on Earth got their start and helps us figure out if life could exist on other worlds. Worlds with anoxic seas, like Europa or exoplanets in the habitable zone, might have conditions similar to Earth in the early days. This could help us figure out how to make other worlds livable. We can learn from the Archean oceans about how planets' environments change over time and how they can support life in very different conditions than today. Lost oceans of the Moon. Ancient lunar water systems. Long thought to be a dry and empty world, the Moon may have had water systems in its early past. New findings of water ice in permanently shadowed craters and signs of hydroxyl molecules on the Moon's surface show that its connection with water is a lot more complicated than was thought before. Because of these discoveries, the interesting idea has grown that the Moon may have had temporary seas or water systems in the past. The Moon formed approximately 4.5 billion years ago, likely as a result of a massive collision between a Mars-sized protoplanet and the young Earth. During its early formation, the Moon's surface was dominated by a magma ocean, a global layer of molten rock. As this ocean cooled and solidified, it is possible that water, delivered by comets or asteroids, became trapped within the lunar crust. Evidence for this hypothesis comes from the discovery of water molecules embedded in volcanic glass beads brought back by the Apollo missions. The presence of hydroxyl, OH, in moon rocks is one of the most convincing proof of ancient water systems there. This chemical signature suggests that during lunar crust development, water was included. Furthermore, found in the permanently darkened areas of moon craters near their poles are deposits of water ice. Preserving ice for billions of years, these craters, which never see sunlight, are naturally cold traps. Transient water systems on the Moon could have been driven by volcanic activity. During periods of intense volcanism, outgassing from the Moon's interior may have released significant amounts of water vapor into the surface environment. This water vapor could have temporarily condensed into liquid water in localized regions, creating transient lakes or shallow seas. However, these conditions would have been short-lived, as the lack of a thick atmosphere and the Moon's low gravity would have caused the water to rapidly evaporate or escape into space. Looking into the Moon's past water systems can help us learn about the early history of the Earth-Moon system. If there was water on the Moon in its early years, it makes us wonder what kind of water the Earth and Moon shared and how they became separated. It also means that water, which is necessary for life, may be more common in the solar system than was thought before. The Artemis program at NASA and international attempts to build a base on the Moon want to study the Moon's polar areas and find out where its water is. Scientists want to figure out how water got to the Moon and whether it could be used as a resource for future travel by looking at where it is found and what it is made of. Ammonia oceans, hypothetical liquid layers in cold gas giants. Ammonia, a compound common in the outer reaches of the solar system, plays a pivotal role in the formation of hypothetical oceans on cold gas giants and their moons. Unlike water, ammonia has a lower freezing point, allowing it to remain liquid at temperatures far below freezing. This unique property makes ammonia-based oceans a plausible phenomenon in environments where water would solidify, opening the door to entirely new types of liquid systems. Ammonia seas are most likely to form where ammonia and water mix, making a slurry of ammonia and water. Depending on how much ammonia is in it, this blend can stay liquid at temperatures as low as -100 degrees Celsius, -148 degrees Fahrenheit, or even lower. People think that this kind of thing can happen on moons like Titan, or even on exoplanets that orbit far from their parent stars. Ammonia not only keeps these seas liquid, but it also changes their physical qualities compared to pure water, like how dense and thick they are. The chemistry of ammonia-based oceans is fundamentally different from that of water oceans. Ammonia acts as a solvent, similar to water, but it facilitates chemical reactions that are not possible in water-based environments. This makes ammonia oceans an exciting prospect for astrobiology, as they could support exotic forms of life. On Earth, certain microbes can metabolize ammonia and survive in environments with high ammonia concentrations, suggesting that similar organisms might thrive in ammonia oceans elsewhere. Ammonia-rich oceans could also exist beneath the surfaces of icy moons in the outer solar system. For example, some models suggest that Titan, Saturn's largest moon, might have an ammonia-rich ocean beneath its icy crust. The presence of ammonia would explain how the ocean remains liquid despite Titan's frigid surface temperatures. Similarly, distant exoplanets with thick ice layers and low temperatures might harbor deep ammonia oceans, insulated from space by overlying ice and gas layers. One interesting thing about ammonia seas is that they might help move heat around the world. Because ammonia can hold a lot of heat, it can move heat quickly through the core of a planet or moon. This could make convection currents move through the ocean, making fluid systems that move heat and nutrients around. These kinds of processes are necessary to keep places livable, even in harsh settings. Ammonia oceans also reveal information about the chemical development of their parent bodies. The presence of ammonia in a planet's or moon's atmosphere can reveal its formation history, as ammonia is more abundant in the outer parts of protoplanetary disks where gas giants and ice moons originate. Studying these seas might shed light on the distribution of volatile chemicals in the early solar system and beyond. Detecting ammonia seas on faraway worlds is difficult, but not impossible. A spectroscopic measurement of light reflected from a planet or moon can reveal ammonia chemical fingerprints in its atmosphere or surface. Transit spectroscopy might detect ammonia vapor in exoplanets' atmospheres, suggesting the presence of an underlying ocean. Radar and infrared investigations of frozen moons may reveal beneath liquid layers, especially if they contain large levels of ammonia. Even though there have been no direct observations of ammonia seas yet, their unique chemistry and ability to make sense in theory make them an interesting subject to study. Future missions to icy moons, like NASA's Dragonfly mission to Titan, might find the first clear proof of liquid systems that are rich in ammonia. Similarly, improvements in tools used to observe other planets may find evidence of ammonia seas on faraway planets. Lava lakes on Io, oceans of molten rock. Io is the most inner of Jupiter's Galilean moons. It is different from every other planet in the solar system. The world is ruled by fire, with more than 400 active volcanoes and huge lava lakes that flow like rivers of molten rock. It is the most geologically active body in the solar system because of how busy its volcanoes are. These volcanoes are caused by Jupiter's strong tides. Its seas of glowing molten rock are very different from the ice oceans of its nearby moons. This gives us a look into the dynamic processes that shape the insides of planets. The largest and most famous of Io's lava lakes is Loki Patera, a volcanic depression over 200 kilometers wide. This massive molten region periodically brightens and dims, an effect thought to be caused by waves of cooling and crustal overturning on the surface of the lava lake. Beneath this surface, immense reservoirs of molten rock feed the lake, replenishing it as it cools. Similar features are seen in smaller lava lakes across Io's surface, many of which are connected to extensive volcanic systems. The volcanoes on Io are heated by the tides, which are caused by the pull of gravity between Io, Jupiter, and Jupiter's moons, Europa and Ganymede. Because Io is orbiting Jupiter, these gravity forces are always pulling and bending it. This causes a lot of friction inside Io, which makes heat that melts rock and keeps the moon's volcanoes going. The scenery is now made up of lava flows, volcanic fields, and tall plumes of gas and ash. The composition of Io's lava lakes offers insights into its interior chemistry. Observations from the Galileo spacecraft and ground-based telescopes have revealed that Io's lava is composed primarily of ultramafic material, rich in magnesium and silicates, with temperatures exceeding 1,600 degrees Celsius, 2,912 degrees Fahrenheit. These high temperatures suggest that Io's mantle is more primitive, retaining the composition of the early solar system. This makes Io a valuable target for understanding the processes that govern the formation and evolution of planetary interiors. Io's lava lakes also interact with its tenuous atmosphere, creating a unique environment where molten rock meets space. Volcanic eruptions release sulfur dioxide gas, which forms a thin, patchy atmosphere around the moon. Some of this gas escapes into space, where it contributes to Jupiter's massive magnetosphere. The interaction between Io's volcanic activity and Jupiter's magnetic field creates powerful auroras, making Io one of the most dynamic moons in the solar system. The lava lakes on Io can be used as a natural laboratory to learn about extreme volcanism. Large lava lakes are rare and short-lived on Earth, but scientists can watch these traits change over time on Io because its volcanoes are always active. We can use what we've learned about Io to help us understand other volcanic worlds, like Venus, and even exoplanets that have a lot of natural activity. Even though Io's surface is not friendly, its molten regions may still be useful for studying life in space. Figuring out the chemical reactions going on in Io's lava lakes might help us understand how volcanic settings affect how the atmospheres of other planets change over time. Even though Io probably doesn't have life on it, its fiery surface could help us learn more about other worlds like it in the universe. NASA's Europa Clipper and ESA's JUICE, Jupiter Icy Moons Explorer, may also study Io, giving us new information about its boiling seas and volcanoes. Dedicated trips to Io, like the planned Io Volcano Observer, could make studies that are closer and more thorough, revealing the secrets of its harsh geology. Oceans of metallic hydrogen in gas giants. Under the thick swirling atmospheres of gas giants like Jupiter and Saturn is a place of extreme heat and pressure where hydrogen changes into solid hydrogen, which is not found on Earth. It is thought that these oceans of metallic hydrogen, which form in very harsh conditions, are very important to the movement of things inside gas giants, affecting everything from their magnetic fields to how heat is distributed. By exploring this mysterious layer, we can learn more about the secret forces that shape some of the solar system's biggest worlds. Metallic hydrogen forms when hydrogen atoms are subjected to pressures exceeding 1 million times Earth's atmospheric pressure. Under these conditions, the hydrogen atoms are forced so tightly together that their electrons become delocalized, behaving more like the electrons in a metal. This transformation turns hydrogen into a highly conductive liquid, capable of transmitting electrical currents and heat with remarkable efficiency. These properties make metallic hydrogen a unique and fascinating state of matter, one that dominates the deep interiors of gas giants. Jupiter is the prime candidate for hosting an extensive ocean of metallic hydrogen. Its immense mass and gravitational force compress its interior to pressures exceeding 3 million times that of Earth's atmosphere. Models of Jupiter's structure suggest that metallic hydrogen begins about 20,000 kilometers below the cloud tops and extends toward the planet's core, forming a layer thousands of kilometers thick. This vast ocean of metallic hydrogen is thought to surround a dense, rocky core, though the exact nature of Jupiter's core remains uncertain. Saturn, while smaller than Jupiter, also likely hosts metallic hydrogen in its interior, though the layer may be thinner due to lower internal pressures. The presence of metallic hydrogen in both planets plays a critical role in generating their magnetic fields. As the metallic hydrogen circulates, it creates powerful dynamo effects, producing the intense magnetic fields that define these gas giants. Jupiter's magnetic field, for example, is the strongest of any planet in the solar system, extending far into space and influencing its moons and surrounding environment. A curious aspect of metallic hydrogen seas is that they might be able to move heat around inside gas giants. Metallic hydrogen is very good at moving heat from the planet's heart to its upper layers because it is a good conductor. This process helps explain the fact that Jupiter gives off more heat than it gets from the Sun. This is called internal heat flow. The metallic hydrogen on Jupiter also affects the convection currents in its atmosphere, which helps to make Jupiter's famous bands and storms. The study of metallic hydrogen is not limited to the gas giants of our solar system. Many exoplanets, particularly hot Jupiters and other massive gas planets, are thought to host metallic hydrogen in their interiors. The behavior of metallic hydrogen under varying pressure and temperature conditions could provide clues about the internal structures of these distant worlds, helping scientists understand their evolution and unique characteristics. While solid hydrogen hasn't been seen directly, experiments on Earth have given us a lot of useful information. Using diamond anvil cells to simulate high-pressure situations similar to those inside gas giants has led to short views of metallic hydrogen. In line with theoretical models, these tests show that metallic hydrogen is steady and has a high conductivity. However, the high pressures needed make it hard to study solid hydrogen in depth, which means that many questions remain unsolved. NASA's Juno mission is already revealing the mysteries of these planets' interiors. Juno's observations of Jupiter's gravitational field, magnetic field, and atmospheric chemistry provide indirect evidence for the presence and behavior of metallic hydrogen. Continued observations and improved models will allow us to better understand this odd condition of matter. Metallic hydrogen seas provide a view into a world of extremes, where everyday components take on remarkable shapes. These seas not only impact the interior dynamics of gas giants, but also show the variety of planetary ecosystems. Diamond rain and oceans on Uranus and Neptune. The solar system's ice giants, Uranus and Neptune, host some of the most severe and interesting environments in the universe. Among their numerous mysteries, the potential of diamond showers and perhaps seas of liquid diamond deep beneath their depths is one of the most astonishing. These strange reactions, fueled by enormous pressure and heat, demonstrate the amazing variety of planetary chemistry and physics. The concept of diamond rain originates from the unique composition of Uranus and Neptune. Unlike Jupiter and Saturn, which are dominated by hydrogen and helium, the ice giants are rich in heavier elements such as carbon, oxygen, nitrogen, and sulfur. Methane, a carbon-based molecule, is particularly abundant in their atmospheres. When exposed to the intense pressures and temperatures found deep within Uranus and Neptune, methane molecules break apart, releasing carbon atoms that bond to form diamond structures. As these diamonds form, they are believed to rain down through the planet's interior, sinking toward its core. This process could create layers of solid diamonds, or even liquid diamond oceans in the lower regions of Uranus and Neptune. The pressures in these regions can exceed 1 million times Earth's atmospheric pressure, while temperatures can soar to thousands of degrees Celsius, conditions sufficient to melt and sustain liquid diamond. Laboratory tests on Earth have produced evidence to support this occurrence. Researchers used high-pressure technologies, like as diamond anvil cells and high-powered lasers, to reproduce the conditions within ice giants. These tests successfully created microscopic diamond crystals from methane under tremendous pressure, providing credence to the theory of diamond production within Uranus and Neptune. Some studies have even proposed that liquid diamond behaves like water, with waves and convection currents moving through the planet's core. The presence of diamond rain and oceans has profound implications for the internal dynamics of Uranus and Neptune. As diamonds sink toward the core, they release gravitational energy, which could contribute to the planet's heat distribution. This energy might help drive convection currents within their interiors, influencing their magnetic fields. Both Uranus and Neptune have unusual magnetic fields, tilted significantly relative to their rotational axes and offset from their centers. The interactions between diamond-rich layers and other materials could play a role in shaping these magnetic fields. These processes also help us understand how ice giants have changed over time. The creation of diamond layers could be a long-term way for carbon and other elements to be moved around inside worlds. Over billions of years, this shift could change Uranus and Neptune's internal makeup and temperature structure, which would add to their unique traits. Beyond the ice giants of our solar system, diamond rain and oceans may be common on exoplanets with similar compositions. Many exoplanets discovered to date fall into the super-Earth and mini-Neptune categories, which are thought to have thick icy mantles and carbon-rich atmospheres. The same high-pressure conditions that create diamond rain on Uranus and Neptune could also exist on these distant worlds, making diamond formation a universal process in planetary interiors. Uranus and Neptune are still some of the least studied worlds in the solar system, even though they are very important. When it flew by these worlds in the 1980s, Voyager 2 was the only ship that could see them up close. The goal of future projects like planned orbiters or probes is to learn more about Uranus and Neptune's atmospheres and how they are built inside. Such trips could help prove that diamond rain exists and give us a better idea of what chemical and physical processes are going on inside these worlds. The concept of diamond rain and seas emphasizes the amazing variety of planetary settings and the unexpected behavior of common elements under very hostile conditions. Often regarded as the forgotten giants of the solar system, Uranus and Neptune have secrets that could transform planetary research. Chameleon oceans, transition zones between ice and liquid. Chameleon seas, which are the unique places where ice and liquid water meet under very high pressure, are some of the most interesting and hard-to-find places in the world. These zones arise on cold worlds where strong pressure drives ice into unusual shapes while letting liquid water endure under. These areas' dynamic chemistry and physics produce possible ecosystems unlike anything else on Earth that provide a window into the variety of liquid systems existing outside our planet. In subsurface oceans, such as those on Europa and Ganymede, the upper layers are composed of solid ice, while the deeper layers contain liquid water. Between these layers lies the transition zone, where pressure and temperature conditions force ice into high-pressure forms, such as Ice 6 or Ice 7. These types of ice are denser than liquid water, and their formation creates a slushy boundary that is neither entirely solid nor fully liquid. This chameleon-like state constantly shifts as thermal and gravitational forces act upon it. As a natural reactor, the transition zone mixes substances from the frozen surface with liquid water underneath. This may produce a dynamic interface full of nutrients and energy sources, maybe sustaining microbial communities. Similar interfaces between solid ice and liquid water, as those seen in polar ice caps or glacial melt zones, are known to support microbial life on Earth. The movement of material within chameleon oceans may also play a critical role in their overall dynamics. Convection currents driven by heat from the planet or moon's interior could circulate water and dissolved minerals through the transition zone, distributing nutrients and maintaining chemical gradients. These processes could create localized hotspots of activity where life might thrive. Observing and studying Chameleon oceans presents a significant challenge, as these regions are buried beneath kilometers of ice. However, radar and seismic instruments on board future missions, such as NASA's Europa Clipper or ESA's JUICE, Jupiter Icy Moons Explorer, could help identify the boundaries of these transition zones. By analyzing the behavior of sound waves as they travel through different layers, scientists can infer the composition and structure of the ice and liquid beneath. There are also effects on exoplanets and their possible habitability that come from studying chameleon seas. There may be similar transition zones on many icy super-Earths and mini-Neptunes. These are places where pressure and temperature make the edges of ice and liquid different from one another. These areas might be a new kind of livable zone, which means that living things could survive in a wider range of conditions. Nitrogen lakes on Triton, oceans of frozen gas. Triton, Neptune's largest moon, is a world of extremes, with surface temperatures dropping to nearly -235 degrees Celsius, -391 degrees Fahrenheit. Despite its frigid conditions, Triton hosts unique nitrogen lakes and frozen gas features that provide a window into the processes shaping icy moons. These nitrogen lakes, formed from volatile compounds, represent one of the most exotic examples of liquid systems in the solar system. Triton's nitrogen lakes are thought to form during its seasonal cycles, as sunlight briefly warms the moon's surface. Unlike Earth's lakes, which are composed of water, Tritons are primarily made of liquid nitrogen, a compound that transitions between solid, liquid, and gas at extremely low temperatures. This process creates a dynamic environment where nitrogen lakes can appear and disappear over time, driven by changes in temperature and pressure. The nitrogen lakes on Triton are closely tied to its atmosphere, which is composed mostly of nitrogen with traces of methane. During warmer periods, sublimation occurs, where nitrogen ice transitions directly into gas, thickening the atmosphere. When temperatures drop, nitrogen condenses back into ice or liquid, creating transient lakes and frost deposits. This unique cycle of nitrogen sublimation and condensation gives Triton's surface its distinctive appearance, with smooth plains and ridges shaped by the movement of frozen and liquid nitrogen. Triton's nitrogen lakes are among its most fascinating characteristics and interact with the volcanic activity of the moon. Triton is renowned for its cryovolcanism, in which liquid nitrogen, water, or another volatile erupt rather than molten rock. These cryovolcanoes might restore the nitrogen lakes and change the surrounding topography, producing patterns and features not found on other moons. Triton's nitrogen lakes are home to some very interesting chemicals that make us wonder if they could support strange processes. Even though it's too cold for water-based life, nitrogen, methane, and other chemicals could react with each other to make complex organic molecules. These molecules could build up in the lakes or get stuck in the ice, which would reveal information about prebiotic chemistry in harsh settings. Detecting and studying Triton's nitrogen lakes presents significant challenges, given its distance and cold conditions. However, future missions to Neptune and its moons could provide valuable insights. A dedicated orbiter or flyby mission equipped with infrared spectrometers and radar could analyze the composition of Triton's surface and atmosphere, revealing the extent and behavior of its nitrogen lakes. The salty oceans of super-Earths, high-pressure chemistry. Super-Earths, which are exoplanets bigger than Earth but smaller than Neptune, are some of the most compelling locations to look for oceans outside of our solar system. A lot of these worlds are thought to have huge oceans that might cover the whole area, but because they are so big and heavy, their conditions are much worse than on Earth. The chemistry and movement of their salty seas are affected by huge forces. The pressure in a super-Earth's ocean would be hundreds or even thousands of times greater than that of Earth's oceans. At these depths, water can take on exotic forms, such as high-pressure ices or supercritical fluids, which exist in a state between liquid and gas. The interaction between these phases creates unique boundary layers that could influence ocean circulation and nutrient transport, possibly supporting life in ways we can only begin to imagine. Salinity plays a critical role in the chemistry of super-Earth oceans. While Earth's oceans are dominated by sodium chloride, the oceans of super-Earths might be rich in other salts, such as magnesium sulfate, potassium chloride, or exotic compounds not found on Earth. These salts could result from differences in planetary formation, the composition of the protoplanetary disk, or interactions with the planet's mantle and atmosphere. The presence of these salts would alter the freezing and boiling points of the ocean, enabling liquid water to persist under extreme conditions. High pressures could also influence the behavior of dissolved gases in super-Earth oceans. For example, carbon dioxide, methane, and other gases might form clathrate hydrates, solid structures in which gas molecules are trapped within water ice. These clathrates could store and release gases over time, influencing the ocean's chemical balance and potentially creating energy sources for hypothetical life forms. Different levels of salt, temperature, and pressure would work together to make super-Earth seas move. Large-scale thermohaline currents that carry heat and nutrients around the world could be caused by these things. On Earth, similar processes are very important for keeping the temperature stable and keeping marine species alive. On a super-Earth, these currents could make places where people could live that are normally very harsh. Finding and studying the super-Earth's salty seas is still a big problem. Today's telescopes, like the James Webb Space Telescope, JWST, can look through the atmospheres of other planets to find signs of water vapor, which could mean that there are oceans on the surface. Future projects that use advanced spectroscopy and direct image technologies might be able to learn more about what these seas are made of and how they behave. Silicate oceans on magma worlds. Silicate seas, which are made up of liquid rock, are some of the harshest places you can imagine. These seas of liquid rock are found on magma worlds, which are planets that are very hot because they are close to stars or because of huge tides. They show how planets form and change violently. By Earth's standards, these silicate seas are not very friendly, but they are necessary to understand how rocky worlds change over time. Magma worlds typically form in tight orbits around their stars, where the intense radiation and gravitational forces strip away atmospheres and heat the surface to thousands of degrees. This creates vast oceans of molten silicates, with temperatures high enough to vaporize rock and drive dramatic chemical interactions. Some exoplanets, such as those classified as lava planets, for example Kepler-78b, are thought to be completely covered by these fiery oceans. The chemistry of silicate oceans is unique, driven by the interaction between molten rock and volatile compounds. Elements such as silicon, magnesium, iron, and oxygen dominate the liquid rock, while gases like sodium, potassium, and silicate vapor escape into the planet's thin atmosphere. These volatile elements form an exosphere of rock vapor, creating a dynamic feedback loop between the ocean and the atmosphere. It's interesting to think about how silicate seas might affect the development of planets. The top of the molten rock cools and forms a crust. This crust may finally cause tectonic action or the volcano to erupt again. The silicate ocean and the planet's core could combine to make gradients that affect the planet's long-term stability and natural activity. Earth is thought to have gone through this process when it was young, when it was covered by a lava ocean after it formed. A lot of the work that keeps silicate seas alive is done by tides, especially on planets that circle their stars close by or that interact with other celestial bodies. For instance, the high tides that happen because of gravitational pull can heat up the core of a planet through friction, which keeps the surface melting. This warmth by the tides may also help explain why some lava worlds have volcanoes that keep erupting. Finding silicate seas on other worlds is hard, but new technologies for observing are opening up new possibilities. The James Webb Space Telescope, JWST, and other instruments can look into the atmospheres of these worlds and find chemical signs that show molten rock is present. Seeing sodium or silicate vapor in the atmosphere of a planet, for example, could mean that there are ongoing lava flows or silicate seas there. Although silicate seas are improbable to sustain life as we know it, their research offers vital new perspectives on the early phases of planetary evolution and the hostile conditions of the cosmos. These blazing oceans highlight the flexibility of natural systems to even the most harsh environments, therefore reminding us of the varied and dynamic character of planets. On magma planets, silicate oceans challenge our conception of what makes up the surface of a planet and draw attention to the amazing variety of settings seen outside Earth. Through research of these harsh environments, scientists may reconstruct the evolution and adaptation narrative of planets against their cosmic environs. Hydrothermal vents in alien oceans, a parallel to Earth's origins. Hydrothermal vents, openings on the seafloor where heated water rich in minerals escapes from the crust, are among the most promising environments for the search for alien life. On Earth, these vents are teeming with microbial and animal life, thriving without sunlight in the deep ocean. Instead of photosynthesis, these ecosystems rely on chemosynthesis, a process that uses chemical reactions to produce energy. Similar conditions could exist in the subsurface oceans of icy moons like Europa and Enceladus, where hydrothermal activity may create habitable environments. The existence of hydrothermal vents on alien worlds is supported by indirect evidence. On Enceladus, the Cassini spacecraft detected plumes of water vapor and ice particles erupting from the moon's south pole. These plumes contained silica nanoparticles, a clear indicator of high-temperature interactions between water and rock. Such interactions suggest the presence of hydrothermal vents on the seafloor of Enceladus's subsurface ocean. Similar activity is hypothesized on Europa, where tidal heating from Jupiter's gravity could drive geological processes at the ocean floor. Hydrothermal vents are particularly intriguing because they provide energy and nutrients in environments that are otherwise isolated from sunlight. On Earth, vents release compounds like hydrogen sulfide and methane, which are used by microbes as a source of energy. In the deep oceans of Europa or Enceladus, similar processes could occur, creating the conditions necessary for life to emerge and persist. The combination of water, heat, and chemical energy makes these vents a prime target for astrobiology. The physical and chemical conditions of hydrothermal vents on alien worlds may differ significantly from those on Earth. The high-pressure environments of subsurface oceans could alter the way vents form and function, potentially creating unique ecosystems. For example, vents on icy moons may release ammonia or other exotic compounds instead of hydrogen sulfide, leading to entirely different forms of chemosynthetic life. Studying these differences could reveal the adaptability of life to extreme conditions. The study of hydrothermal vents on alien worlds also has implications for understanding the origins of life on Earth. Many scientists believe that life on our planet began around hydrothermal vents, where the combination of water, heat, and chemical gradients created the perfect conditions for the first microbes to form. By studying similar environments elsewhere in the solar system, we may gain insights into the processes that led to the emergence of life and the potential for it to arise elsewhere. Exotic life in Titan's methane lakes. Could life breathe methane? Titan, Saturn's largest moon, is home to a unique environment that challenges our understanding of habitability. Unlike Earth's water-based ecosystems, Titan's surface features vast lakes and seas of liquid methane and ethane. These hydrocarbon-rich bodies of liquid, combined with the moon's thick nitrogen atmosphere and complex organic chemistry, make Titan a fascinating candidate for exploring the potential of exotic life forms that could thrive in methane-based environments. The chemical and physical conditions of Titan's methane lakes are vastly different from those of Earth's oceans. With surface temperatures hovering around -179 degrees Celsius, -290 degrees Fahrenheit, water exists only as solid ice, while methane and ethane remain liquid. These hydrocarbons are essential components of Titan's hydrological cycle, functioning much like water does on Earth. Methane evaporates, forms clouds, and falls back to the surface as rain, replenishing Titan's lakes and shaping its dynamic landscape. The possibility of life in Titan's methane lakes hinges on the idea that life could adapt to use methane as a solvent instead of water. On Earth, water is the foundation of all known life, facilitating chemical reactions and serving as a medium for transporting nutrients. However, some scientists propose that life could evolve to metabolize hydrocarbons using methane and ethane as solvents in their biochemistry. In such an ecosystem, instead of exhaling carbon dioxide as a waste product, organisms might release methane or acetylene. The Huygens probe, which landed on Titan in 2005, provided the first direct evidence of the Moon's surface conditions, including the presence of methane lakes and a complex array of organic molecules. Subsequent observations by the Cassini spacecraft revealed the composition and distribution of Titan's lakes, as well as the presence of acetylene, hydrogen cyanide, and other organic compounds. These molecules are considered building blocks for life, raising the possibility that prebiotic or even biological processes might occur in Titan's lakes. One of the most intriguing pieces of evidence for the potential of life on Titan comes from an observed depletion of hydrogen and acetylene near the Moon's surface. On Earth, microbes consume hydrogen in chemical reactions, so some scientists speculate that similar processes could occur on Titan. However, this hypothesis remains highly speculative, as abiotic processes might also explain the observed chemical patterns. If life does exist on Titan, it would represent a form of biology entirely different from anything found on Earth. Such life would expand our understanding of habitability, demonstrating that life can adapt to environments previously thought uninhabitable. This discovery would have profound implications for the search for life elsewhere in the universe, suggesting that habitable worlds may not need to resemble Earth. Titan's lakes may not have any living things in them, but they still teach us a lot about primitive chemistry and the conditions that life needs to start. Scientists can learn more about the different kinds of chemical reactions that happen on icy moons and exoplanets by looking at Titan's methane lakes. This helps them figure out if life could exist in places far beyond Earth. Alien aquifers. Can subsurface liquid layers harbor microbial life? Under the frozen surfaces of planets and moons, there may be secret pools of flowing water called alien aquifers that could support life. Because these layers of liquid below the surface are not affected by what's on the surface, they could provide safe places for microbial communities to grow away from the sun. It is thought that alien springs can be found in many places in the solar system and beyond. This opens up interesting options for living in places that were thought to be uninhabitable in the past. On Earth, aquifers exist deep underground, where they provide habitats for microbes that survive entirely on chemical energy. These microbes, known as chemolithoautotrophs, extract energy from inorganic compounds such as hydrogen, sulfates, and iron, rather than relying on sunlight. If similar processes occur elsewhere, alien aquifers could host life even in environments that lack surface water or atmospheric protection. Mars is among the most likely sites for extraterrestrial aquifers in the solar system. Radar observations of the Mars Express mission of the European Space Agency indicated the possible existence of a liquid water lake under the South Pole ice cover. A mix of salts and geothermal heat might keep this lake, buried under 1.5 kilometers of ice, liquid. Should confirmation, it would be a stable habitat far from the hostile surface conditions of Mars where microbial life may flourish. Other icy moons, such as Europa and Enceladus, may also harbor aquifers within their crusts. These moons are already known for their subsurface oceans, but localized pockets of liquid water could exist closer to the surface. On Europa, cracks in the ice shell might allow water to seep into shallow aquifers, where it interacts with minerals and organic molecules. These aquifers could provide temporary habitats for microbes, especially if they are periodically replenished by the larger ocean below. Alien aquifers may also exist on moons like Titan, where a subsurface ocean of water and ammonia lies beneath a thick icy crust. Localized aquifers within the crust could form when ammonia-rich water becomes trapped in pockets, creating chemically distinct environments. The presence of ammonia as an antifreeze could further expand the range of habitable conditions, allowing water to remain liquid at extremely low temperatures. The discovery of subsurface liquid layers has significant implications for astrobiology. These environments are shielded from surface radiation and extreme temperature fluctuations, providing long-term stability for life. They may also facilitate chemical interactions between water, minerals, and organic compounds, creating conditions favorable for the emergence of life. On Earth, similar subsurface ecosystems have been found kilometers below the surface, thriving in environments with no connection to sunlight. It is quite difficult to detect extraterrestrial aquifers. Radar devices can detect liquid water layers on frozen worlds by penetrating their crust and analyzing their conductivity and reflection characteristics. The use of thermal imaging can also help pinpoint potential sources of localized heat that could support liquid water. While further in-depth investigation is necessary for proof, ground-penetrating radar has previously hinted about aquifers on Mars. Future rovers and the planned drilling mission ExoMars could try to take samples of Martian soil from the surface. Europa Clipper and any future landers equipped with radar might scan Europa's icy exterior and locate liquid water pockets on Enceladus. Critical proof for the habitability of these hidden ecosystems might be provided by instruments that detect chemical traces, such salts or organic compounds. Alien aquifers test our knowledge of habitability by broadening the spectrum of conditions in which life may exist. They show that life is not limited to a planet with surface seas and an Earth-like temperature, but can adapt to hidden, isolated pockets of liquid water. Scientists believe that by examining these subterranean layers, they will find not just signs of life, but also information about the processes that allow it to flourish under severe environments. Magnetohydrodynamic life forms in electrically conductive oceans. The thought of magnetohydrodynamic life forms in electrically conductive seas is very different from what we normally think about life in the world. If these made-up creatures lived in seas that were high in ions or metals, they might be able to use electrical conductivity and magnetic fields as part of their biology to move, communicate, or make energy. This kind of life would be a whole new branch of biology, able to survive in harsh conditions like nothing else on Earth. Electrically conductive oceans are thought to exist in various locations across the solar system and beyond. Subsurface oceans on moons like Europa and Ganymede, rich in salts, exhibit high levels of conductivity due to the dissolved ions in the water. Similarly, the oceans of metallic hydrogen hypothesized to exist deep within gas giants like Jupiter and Saturn could provide an environment where electromagnetic forces dominate. Life in these environments would need to operate in fundamentally different ways than life on Earth. On our planet, organisms rely on chemical energy and sunlight to fuel their metabolisms. In an electrically conductive ocean, magnetohydrodynamic lifeforms might use the interaction between magnetic fields and electrical currents to sustain themselves. For example, they could generate movement by creating localized currents that interact with the planet's or moon's magnetic field, propelling them through the liquid medium. The magnetic environments of these planets and moons would play a crucial role in shaping the behavior of such life forms. On Europa, for example, the interaction between Jupiter's powerful magnetosphere and the moon's salty subsurface ocean generates electromagnetic currents. Magnetohydrodynamic organisms could exploit these currents, either passively by aligning themselves with existing fields, or actively by creating their own electrical charges to navigate or locate resources. Communication between such organisms might also rely on electromagnetic signals. On Earth, certain species, like electric fish, use electrical pulses to communicate or navigate. Magnetohydrodynamic lifeforms could take this concept further, using complex electromagnetic patterns to convey information or coordinate behavior within their communities. These signals would likely be influenced by the surrounding magnetic environment, creating a dynamic system of interaction. The potential biochemistry of magnetohydrodynamic lifeforms raises fascinating questions. Their cellular structures might incorporate conductive materials, such as metals, into their membranes or skeletons, allowing them to interact with electrical currents. Alternatively, they might use ion gradients more effectively than Earth-based life, taking advantage of the high salinity and conductivity of their environment to generate energy. These adaptations would depend on the specific conditions of their oceans, such as pressure, temperature, and magnetic field strength. Finding magnetohydrodynamic life is very hard, because their signs and moves may be very weak and hard to tell apart from electromagnetic noise in the background. Instruments that can measure electromagnetic activity, like magnetometers and plasma wave monitors, might show signs of these living things in a roundabout way. Future trips to moons like Europa and Ganymede could also send robots or submersibles that can study the electrical properties of the ocean. This would allow scientists to look for strange things that might mean there is life there. Beyond the solar system, electrically conductive oceans could exist on exoplanets with unique atmospheric or geological compositions. Many super-Earths and mini-Neptunes are thought to host thick layers of water and ice, where pressure and temperature create conditions for conductive oceans. These planets, especially those with strong magnetic fields, represent intriguing targets for studying the potential for magnetohydrodynamic life. The idea that living things have adapted to seas that carry electricity goes against what we normally think about biology and habitability. It increases the number of places where life could survive and shows how life can adapt to harsh conditions. Scientists learn more about the different kinds of life in the world and the creative ways it might have evolved to stay alive by looking into these options. Deep ocean currents and their role in distributing nutrients. Deep ocean currents are essential for sustaining life in Earth's oceans, as they distribute nutrients, regulate temperatures, and maintain chemical balance. In extraterrestrial oceans, these currents might play a similar role, creating habitable zones and supporting potential ecosystems. By examining the dynamics of deep ocean currents on other planets and moons, we can better understand their potential for sustaining alien life. Extraterrestrial oceans, such as those beneath the icy crusts of Europa and Enceladus, are shaped by unique forces that drive their circulation. On Earth, ocean currents are influenced by wind, temperature gradients, and the planet's rotation. On icy moons, currents are likely driven by tidal forces from their parent planets. For example, Europa's orbit around Jupiter generates immense gravitational stresses that heat its interior and create convective flows within its ocean. These flows transport heat and nutrients, preventing the ocean from freezing solid and potentially supporting life. Temperature and salinity gradients are also critical factors in driving deep ocean currents. On Earth, thermohaline circulation, a global system of deep currents, is powered by differences in water temperature and salinity. In alien oceans, similar processes could occur, particularly in environments where water interacts with the icy crust or the rocky mantle below. For instance, hydrothermal vents on the seafloor could release warm, mineral-rich water into the ocean, creating localized currents that distribute heat and nutrients throughout the system. The interaction between extraterrestrial oceans and their overlying ice shells adds another layer of complexity. On Europa, fractures in the ice allow water to upwell from the ocean below, potentially carrying nutrients to the surface. This exchange between the ocean and ice could create dynamic currents that cycle materials through the subsurface environment. These currents might also interact with plumes, such as those observed on Enceladus, where water and organic molecules are ejected into space. The presence of such activity suggests a robust circulation system capable of sustaining chemical gradients and energy flows. The chemical composition of extraterrestrial oceans is another critical factor in their potential to support life. On Earth, deep ocean currents distribute essential nutrients such as nitrogen, phosphorus, and iron, which sustain marine ecosystems. In alien oceans, the availability of nutrients would depend on interactions with the rocky core or ice shell. Hydrothermal vents and chemical reactions at the ocean floor could release minerals and compounds into the water, creating nutrient-rich zones that might support microbial life. Exoplanets provide exciting opportunities for investigating deep ocean currents. A lot of super-Earths and mini-Neptunes are thought to have large oceans, and some of them might have thick atmospheres or layers of ice on top of them. The planet's gravity, spin, and heat sources could change the way these layers and the oceans below them move and interact, creating new circulation patterns. Someday, advanced telescopes like the James Webb Space Telescope, JWST, might be able to find signs in the atmosphere or oceans that point to these processes. The role of deep ocean currents in extraterrestrial habitability cannot be overstated. By distributing heat and nutrients, these currents create stable environments where life could emerge and persist. They also maintain chemical gradients, which are essential for driving biological and geological processes. Understanding these dynamics not only enhances our knowledge of alien oceans, but also provides insights into the factors that make a planet or moon suitable for life. Extreme biochemistry in sulfuric acid oceans. Sulfuric acid oceans, while entirely inhospitable to Earth-based life, may exist on certain exoplanets or moons with unique atmospheric and geological conditions. These extreme environments, dominated by corrosive chemistry and high acidity, challenge traditional notions of habitability. However, they also raise intriguing possibilities for exotic forms of life adapted to such harsh conditions. Sulfuric acid oceans could form on planets or moons with abundant volcanic activity, where sulfur compounds are released into the atmosphere and interact with water. Venus provides an example of a world with a highly acidic atmosphere, though its surface is too hot for liquid oceans to exist. On cooler planets, similar processes could result in oceans where sulfuric acid serves as the primary liquid medium, creating a chemical environment vastly different from that of Earth. The biochemistry required to survive in sulfuric acid oceans would be radically different from that of Earth's life forms. Organisms in such environments would need to evolve protective mechanisms against extreme acidity, possibly incorporating acid-resistant proteins and membranes into their cellular structures. On Earth, extremophiles such as acidophilic bacteria thrive in highly acidic environments, such as sulfur-rich hot springs and mine drainage systems. These organisms use sulfur compounds for energy, providing a potential analog for life in sulfuric acid oceans. The nature of sulfuric acid seas would affect how well they could support life. Solubilizing sulfuric acid is different from water. It makes chemical processes easier that might not happen in water-based settings. These processes might make energy differences and nutrient cycles that microbes need to stay alive. For example, the reduction and oxidation of sulfur molecules could be a way to get metabolic energy, like how some bacteria on Earth use iron or sulfur for chemosynthesis. New developments in spectroscopy may help us find ways to find sulfuric acid lakes on other worlds. Seeing signs in the air like sulfur dioxide, water vapor, and other sulfur molecules could mean that the seas are acidic. Planets that circle stars that aren't very bright, like red dwarfs, are especially good options because their cooler temperatures might make it possible for liquids to stay stable even though they are around corrosive chemicals. Astrobiology is greatly helped by the occurrence of sulfuric acid seas. Although they depict some of the most severe settings one could find, they also show the amazing flexibility of chemistry and the possibility for life to change in ways we would never have imagined. These seas serve as a reminder that the spectrum of possibilities molded by the variety of planetary conditions defines, rather than a set idea, for habitability. Radiation-adapted life in high-energy oceans. High-energy oceans, bathed in intense radiation, represent one of the most extreme environments in the universe. These oceans, exposed to high levels of ionizing radiation from their parent stars or surrounding cosmic events, might seem uninhabitable. Yet, the possibility of radiation-adapted life challenges this notion, highlighting the resilience of life in the most unexpected places. Such oceans might exist on planets orbiting close to active stars or in regions of high cosmic ray exposure, such as neutron stars near pulsars are neutron stars. Without a thick atmosphere or magnetic field to shield the surface, these oceans would be bombarded by radiation, altering their chemical and physical properties. The energy from this radiation could drive unique chemical reactions, producing a rich environment for potential life. Radiation-adapted life forms, known as radiotrophs, could harness radiation as a source of energy. On Earth, certain microbes such as Deinococcus radiodurans are capable of surviving extreme radiation levels by repairing DNA damage and using radiolytic products for metabolism. In high-energy oceans, similar adaptations might enable life to not only endure radiation, but also thrive in its presence. The chemistry of high-energy oceans would be distinct, shaped by the constant interaction between radiation and water molecules. This interaction produces reactive oxygen species and other byproducts, which can drive chemical gradients and create new compounds. These gradients might provide the energy needed for life to emerge, similar to how hydrothermal vents on Earth create nutrient-rich environments for deep-sea organisms. Detecting high-energy seas and their possible biosignatures is a tricky challenge. Instruments that can analyze the spectra of exoplanet atmospheres may detect unexpected chemical indicators such as elevated quantities of hydrogen peroxide or other radiolytic products. Observing the planet's radiation environment, including emissions from its parent star, can also assist determine if such seas exist. Radiation-adapted life research is important for more than just astrobiology. It tells us about the limits of life on Earth and the chance that life could escape terrible cosmic events like supernovae or gamma-ray bursts. Figuring out how life can survive in places with a lot of radiation also helps us look for life in other difficult places in our solar system, like the surface of Europa or the oceans below the surface of Enceladus. Eris and Sedna. Could Kuiper Belt objects hide tiny oceans? People who talk about planetary seas often forget about Eris and Sedna, which are faraway objects in the Kuiper Belt and scattered disk. These cold worlds are found far beyond Neptune and have temperatures so low that liquid water doesn't seem to be possible. However, the idea that seas exist below the surface and are heated by heat inside and insulated by layers of ice is still an interesting one. Eris, the second largest known dwarf planet in the solar system, has a highly reflective surface composed primarily of frozen methane. Its extreme distance from the Sun, averaging 96 AU, results in surface temperatures as low as -243 degrees Celsius, -405 degrees Fahrenheit. Yet beneath this icy crust, Eris might conceal a liquid ocean. The potential for such an ocean arises from radiogenic heating, heat generated by the decay of radioactive isotopes within Eris's core. Over billions of years, this heat could maintain a thin layer of liquid water beneath the thick ice shell, insulated from the extreme cold of space. Sedna, another distant object with an elongated orbit that takes it as far as 937 AU from the Sun, presents a similar case. With a surface composed of frozen nitrogen and methane, Sedna appears lifeless and inert. However, its large size and suspected rocky core could provide enough heat to sustain a subsurface ocean. Additionally, tidal interactions with the Sun during its perihelion, when it comes closest to the Sun, might generate additional heat, temporarily influencing its interior dynamics. The insulating effect of Eris and Sedna thick ice coatings is one of the main elements determining whether subterranean seas there can be. Acting as a barrier, ice keeps steady temperatures under the surface by stopping heat from escaping. Within these far-off worlds, this insulation and the internal heat produced by radiogenic decay might produce a limited but constant livable zone. The potential chemistry of these oceans is also intriguing. Unlike the saline oceans of Europa or Enceladus, the liquid layers on Eris and Sedna would likely be rich in ammonia and other antifreeze compounds, which lower the freezing point of water. This could result in highly unusual chemical environments, where life, if it exists, would need to adapt to extreme cold and high concentrations of ammonia. It is very hard to find oceans below the top of these faraway things. Because they are so far away, it is hard to look at them directly, and modern telescopes don't have enough precision to study their innards in detail. Future trips to the Kuiper Belt, however, with improved radar and spectroscopic tools, might be able to help find out if these icy worlds hide oceans. First hints could come from indirect evidence, like features on the surface that point to cryovolcanism or chemical signs of action below the surface. Oceans without atmospheres, subsurface seas on rogue planets. Rogue planets, drifting alone in interstellar space without the warmth of a host star, may seem like unlikely candidates for liquid water. Yet some of these dark wanderers could harbor subsurface oceans, insulated from the cold of space by thick layers of rock and ice. The idea of oceans existing on worlds with no atmosphere or sunlight challenges traditional notions of habitability and highlights the adaptability of water in the universe. Rogue planets are thought to form in planetary systems, but are later ejected by gravitational interactions, sending them careening through interstellar space. Without a parent star, these planets rely on internal heat sources to maintain liquid water. Radiogenic decay within the planet's core can provide a steady source of heat, preventing water from freezing entirely. In larger rogue planets, the immense pressure created by thick ice layers may further insulate liquid oceans, trapping heat and sustaining conditions for billions of years. The absence of an atmosphere on a rogue planet poses significant challenges for habitability. Without an atmospheric blanket to regulate temperatures, surface conditions would be unimaginably cold. However, subsurface oceans could remain stable, shielded from the vacuum of space by a thick outer shell of ice and rock. These oceans would be entirely cut off from external energy sources, relying solely on geothermal heat and potentially tidal forces if the planet hosts one or more moons. A fascinating thing about the deep seas on rogue worlds is that they might be able to support life. Deep below the Earth's surface, in places like aquifers and hydrothermal vents where sunshine never gets through, life grows. Similar situations might happen on rogue planets, where microbial communities could be supported by chemical energy from the interaction between water and the planet's hard core. Instead of getting energy from sunshine, these living things would use chemosynthesis, which uses chemicals like hydrogen and sulfur. The chemistry of rogue planet oceans would likely differ significantly from Earth's. In the absence of atmospheric interaction, these oceans might be dominated by minerals leached from the rocky mantle, creating unique chemical gradients. Additionally, the pressure and temperature conditions within these oceans could allow for the formation of exotic phases of ice and water, further diversifying their environments. Finding seas on rogue worlds is a very difficult task. Because these planets don't give off light, they are hard to see directly. But more modern cameras and devices could find rogue planets by picking up their faint infrared emissions, which come from the heat inside them. Gravitational microlensing, a process by which a planet's gravity briefly increases the light of a nearby star, could also tell us about their size, makeup, and ability to hold liquid water. Rogue planets with subsurface oceans could also produce indirect signatures of habitability. For example, interactions between the ocean and the planet's magnetic field might create electromagnetic signals detectable by space-based observatories. Additionally, if the planet retains even a thin atmosphere, gases like water vapor or methane might escape from cracks in the ice, offering a hint of the hidden ocean below. The study of rogue planets has profound implications for understanding the limits of habitability. These isolated worlds demonstrate that liquid water can persist even in the absence of sunlight or an atmosphere, expanding the range of environments where life might exist. They also provide insights into the resilience of water as a medium for life, capable of adapting to conditions that seem completely alien to us. Slushy ice oceans under mid-pressure worlds. Mid-pressure worlds, planets or moons with conditions that blur the line between solid and liquid phases, offer a unique and little explored type of ocean environment. In these worlds, ice and water coexist in a slushy, semi-liquid state, creating complex layered systems that challenge our understanding of planetary dynamics and habitability. These slushy oceans arise in regions where pressure and temperature interact in ways that prevent water from becoming entirely solid or liquid. The slushy layers on mid-pressure worlds are thought to form in environments where gravitational forces and thermal energy maintain an intermediate state of matter. For instance, icy moons such as Europa and Ganymede may host slushy zones between their solid ice crusts and fully liquid oceans. These layers result from gradual temperature and pressure gradients, where heat from the core or tidal interactions keeps the water from freezing entirely, while the overlying pressure of the ice crust prevents the water from becoming fully liquid. One remarkable element of slushy oceans is their distinct physical characteristics. The semi-solid condition allows for gradual but continuous movement of material, similar to the flow of glaciers on Earth. This movement can assist the flow of nutrients and minerals, resulting in dynamic ecosystems that may sustain life. Furthermore, the slushy layers function as a thermal and chemical buffer, reducing temperature swings and allowing substances to mix between the solid and liquid zones. Chemically, slushy oceans may be rich in salts, ammonia, and other antifreeze compounds, which lower the freezing point of water and maintain the semi-liquid state. These compounds can create distinct chemical gradients, which are essential for driving biological and geological processes. On Earth, similar gradients are found in subglacial lakes, where microbial ecosystems thrive despite extreme conditions. The study of these Earth analogues provides valuable insights into the potential habitability of slushy layers on other worlds. Slushy oceans could also play a significant role in the geological evolution of mid-pressure worlds. The interaction between the semi-liquid layers and the overlying ice crust might drive surface activity, such as the formation of ridges, cracks, and other features. On Europa, for example, the movement of slushy material beneath the ice could explain some of the Moon's surface patterns. These interactions highlight the dynamic nature of slushy oceans and their influence on planetary geology. It's interesting to look into whether there is life in wet seas. Even though these places may seem like they have harsh conditions, life on Earth has shown itself to be very flexible. Under ice lakes, polar ice caps, and pockets of salty water have all been found to have microbes. These places are a lot like the slushy layers that scientists think might exist on other planets. The layers' slow movement and chemical reactions could make places where simple animals could do well. Detecting slushy oceans is a difficult undertaking that necessitates modern tools. Ice-penetrating radar, seismometers, and thermal photography can all help us understand the structure and behavior of these layers. Future missions, such as NASA's Europa Clipper and the European Space Agency's JUICE, are designed to examine Jupiter's ice-covered moons in detail, perhaps revealing slushy zones within their underlying habitats. Slushy layers on exoplanets may be identified by observatories based on their atmospheric composition or thermal fingerprints. The notion of slushy seas broadens the spectrum of settings in which liquid water, and maybe life, can exist. These transitional zones call into question established notions of habitability, highlighting water's flexibility to a variety of situations. By investigating the distinct features of slushy layers, we get a better understanding of the mechanisms that build frozen planets and their ability to host life. Deep ocean basins of distant dwarf planets. Dwarf planets like Orcus, Haumea, and Quaoar, which are located in the furthest parts of the solar system, are frequently ignored when people talk about ocean worlds. However, these ice worlds, which are located in the Kuiper Belt, could have deep ocean basins concealed beneath their frozen surfaces. By studying these basins, we can get an idea of the possibility of liquid water existing well outside of the usual habitable zone. The possibility of subsurface oceans on distant dwarf planets arises from a combination of internal heating and insulating ice layers. Radiogenic decay within the rocky cores of these bodies provides a steady source of heat, while their thick ice shells trap this heat, preventing the liquid layers from freezing. The presence of ammonia and other antifreeze compounds in the ice further lowers the freezing point of water, increasing the likelihood of liquid reservoirs. Haumea, known for its elongated shape and rapid rotation, is a particularly intriguing candidate. Its surface shows evidence of water ice, and its unusual thermal properties suggest internal activity. The tidal forces generated by its moons may also contribute to heating, creating conditions conducive to liquid water beneath its icy crust. Orcus, often referred to as a twin of Pluto due to its similar size and orbital characteristics, also shows promise as a potential ocean world. Observations of its surface reveal traces of volatile compounds, including methane and carbon dioxide, which may be linked to subsurface reservoirs of liquid water. Orcus's moon, Vanth, could play a role in generating tidal heating, further enhancing the possibility of an ocean beneath its surface. The chemistry of these deep ocean basins would likely be influenced by interactions between the water and the rocky cores of the dwarf planets. Hydrothermal activity at the water-rock interface could release minerals and nutrients into the ocean, creating chemical gradients that might support microbial ecosystems. Similar processes occur on Earth at deep-sea hydrothermal vents, where life thrives despite the absence of sunlight. It would be hard, but new telescope technology and spaceflight might make it possible for us to find out if these other worlds have seas below their surfaces. Infrared and radio studies can help find surface features and heat oddities that could be signs of activity inside. It's possible that future trips to the Kuiper Belt with radar and spectroscopic sensors could reveal the size and type of these dwarf planets' hidden seas. This is because they would be able to directly study their structure and makeup. The deep ocean areas of faraway dwarf planets make the places where liquid water could live bigger. They make us question what we think we know about habitability and show us the huge range of conditions that can keep liquid systems alive. Transient oceans on comets, short-lived water systems. Comets, often described as dirty snowballs, are typically associated with frozen water and dust. However, as they approach the Sun, these icy bodies undergo dramatic transformations, temporarily creating transient oceans or liquid water systems beneath their surfaces. These ephemeral reservoirs, though short-lived, provide valuable insights into the behavior of water in extreme environments and its potential role in the evolution of organic compounds. As comets travel along their elliptical orbits, solar radiation heats their surfaces, causing the frozen ices to sublimate directly into gas. Beneath the surface, however, the heat can penetrate just deep enough to create pockets of liquid water, insulated by the overlying ice. This process is thought to occur in larger comets, where the size and composition of the nucleus allow for sufficient heat retention. The Rosetta mission study of Comet 67P/Churyumov-Gerasimenko in unprecedented detail is one of the most convincing examples of water systems that change over time. On the comet's surface, the mission found complex organic chemicals and signs of localized heat. These results show that liquid water might exist briefly below the surface, reacting with organic matter and possibly making conditions good for prebiotic chemistry. The chemistry of these transient oceans is unique, driven by the interaction between water, volatile compounds, and organic material. Comets are rich in carbon-based molecules, such as methanol, formaldehyde, and amino acids. When water melts and mixes with these compounds, it can trigger chemical reactions that form more complex molecules. These reactions are thought to be similar to the processes that occurred on the early Earth, making comets valuable analogues for studying the origins of life. The formation of transient oceans on comets also has implications for planetary science. When comets collide with planets or moons, they can deliver not only water, but also the organic compounds formed in their liquid pockets. This delivery system may have played a crucial role in seeding early Earth with the building blocks of life. The same process could occur on other worlds, such as Mars or Europa, where impacts from water-rich comets contribute to the planet's inventory of volatile compounds. To find temporary seas on comets, you have to pay close attention to them when they are busy. Comets can be studied up close with missions like Rosetta, or they can be watched from afar with ground-based cameras and space stations. Future trips to comets, which might include landers or sample return missions, could give us even more information about how water and organic matter behave in these icy things. Oceans beneath the surface of centaurs. There is a mysterious group of icy objects in the solar system called centaurs. They have features of both asteroids and comets, making them very interesting. These strange bodies, which orbit between Jupiter and Neptune, are thought to have oceans below their frozen surfaces. Centaurs aren't given much attention in planetary science, but studying their secret layers of liquid might assist us understand how water stays alive in harsh settings. Centaurs, such as Chiron and Chariklo, are composed of a mix of rock, ice, and volatile compounds. Their surfaces show evidence of water ice and organic materials, hinting at dynamic processes beneath the surface. The possibility of subsurface oceans arises from a combination of radiogenic heating, caused by the decay of radioactive isotopes in their cores, and the insulating effect of their ice-rich exteriors. These factors could allow liquid water to persist for billions of years, despite the low temperatures of the centaur's orbits. The centaur's ability to demonstrate comet-like behavior on occasion is one of its most fascinating traits. Some centaurs, like Chiron, have been seen to release dust and gas, which is usually seen in comets. This phenomenon is consistent with the idea that water and other volatile substances are occasionally released from underground reservoirs through cracks or cryovolcanic vents. Localized heating, or the slow accumulation of pressure in the subsurface strata, might be the driving forces behind these eruptions. Chariklo, the largest known centaur, adds another layer of mystery with its ring system. Discovered in 2014, these rings are thought to consist of icy particles, potentially sourced from cryovolcanic eruptions or impacts. The presence of these rings raises questions about the internal structure of Chariklo and whether its subsurface layers include liquid water or slushy reservoirs capable of ejecting material into space. Centaur C's molecules would be unique from that of other frozen worlds, shaped by their solar system position and volatiles mix in composition. Other antifreeze substances, such ammonium, methane, and ammonium, might reduce the freezing point of water, therefore providing stable surroundings for liquid reservoirs. These reservoirs could also include organic molecules, which over time might undergo complicated chemical interactions and perhaps produce prebiotic chemicals. Given their distance and tiny scale, finding Cs on centaurs presents great difficulties. By use of spectral signature analysis, instruments equipped to detect water ice, organic molecules, and volatile activities provide hints on the existence of liquid layers under the surface. The study of centaurs bridges the gap between asteroids, comets, and icy moons, highlighting the diversity of environments where liquid water might exist. By exploring these hybrid objects, scientists can uncover new details about the processes that sustain water in the outer solar system and expand the search for habitability in unexpected places. Thermohaline currents in salty exoplanet oceans. Thermohaline currents driven by differences in temperature and salinity are vital for circulating nutrients and maintaining life in Earth's oceans. On exoplanets with large salty oceans, these currents could play a similar role, creating dynamic and potentially habitable environments. Understanding how these currents operate in alien seas offers insights into the processes that might sustain life beyond Earth. Thermohaline circulation occurs when variations in temperature and salinity cause differences in water density. On Earth, warm, salty water tends to sink in cooler regions, creating deep currents that transport heat and nutrients across the planet. In exoplanetary oceans, similar processes could be influenced by unique conditions, such as exotic chemical compositions, extreme temperatures, or gravitational interactions with nearby moons or stars. On ocean-covered exoplanets known as water worlds, thermohaline currents could drive global circulation patterns, distributing energy and nutrients throughout the ocean. These currents might be particularly significant on planets with thick atmospheres or high surface pressures, where limited heat from a star penetrates to the surface. In such cases, heat generated by geothermal activity or tidal forces could create localized hotspots, driving the currents that circulate nutrients and support potential ecosystems. Salinity gradients could also vary significantly on exoplanets depending on the planet's chemistry and formation history. Oceans rich in salts like magnesium sulfate, ammonia, or other exotic compounds might exhibit entirely different thermohaline dynamics compared to Earth's oceans. These unique gradients could create distinct chemical environments, fostering microbial life adapted to extreme conditions. It's hard, but not impossible, to find thermohaline currents on faraway exoplanets. Advanced telescopes like the James Webb Space Telescope, JWST, may be able to pick up signs in the atmosphere that point to action in the oceans. For instance, changes in the makeup of the atmosphere might show that there are circulation patterns that cause gases to move between the water and the atmosphere. In the future, space-based telescopes might also be able to find heat signals or magnetic oddities that are connected to the movement of the oceans. Finding out about thermohaline currents on other planets is important for astrobiology and the search for worlds where living things could survive. Scientists can better figure out if there is life in alien seas and improve models of exoplanet temperatures if they know how these currents work. It's possible that these currents also help keep ocean-covered worlds stable over long periods of time, making sure that people can live in their seas. Oceans in perpetual twilight, worlds with eternal night sides. On tidally locked planets, where one side always faces its star and the other remains in perpetual darkness, oceans exist under extreme and unusual conditions. These worlds, common among exoplanets orbiting red dwarf stars, feature stark temperature contrasts between their day and night sides. The interplay of heat and cold creates unique thermal and chemical dynamics in their oceans, offering a new perspective on planetary habitability. The perpetual night side of a tidally locked planet experiences no direct sunlight, leading to freezing conditions and the potential for ice-covered oceans. However, heat from the day side, distributed by atmospheric and oceanic currents, could keep parts of the night side ocean in a liquid state. This constant circulation of energy helps moderate the extreme temperatures across the planet, creating transition zones or terminator regions, where life might thrive. These terminator zones, situated between the scorching day side and the frozen night side, are particularly intriguing. Here, the balance of heat and cold creates stable environments where oceans could remain liquid. Winds and ocean currents driven by the temperature gradients transport heat from the day side, preventing the oceans in these regions from freezing completely. Such zones could harbor unique ecosystems adapted to constant twilight conditions. The chemistry of seas that are always at night would be very different from the chemistry of oceans on Earth. On the night side, less sunshine might make it harder for top nutrients to reach, while deeper areas might need geothermal or tidal warmth to keep the water moving. Because of the big changes in temperature, strange chemical shifts could make places for microbes to live. Life in these seas from other worlds might change over time to use chemical energy instead of photosynthesis. Understanding oceans on tidally locked planets requires innovative observation techniques. Infrared observations from telescopes like the James Webb Space Telescope, JWST, can detect temperature distributions across a planet's surface, revealing the extent of liquid water regions. Additionally, atmospheric signatures, such as water vapor and carbon dioxide, can provide indirect evidence of oceanic circulation and habitability. The potential for life in these twilight oceans challenges traditional notions of habitability, where stable climates and consistent sunlight are often considered essential. These worlds demonstrate that life might thrive under dynamic, extreme conditions, driven by the interplay of heat, cold, and chemistry. By studying such planets, we broaden our understanding of where life might exist and the diverse environments that could support it. Under ice drones, exploring subsurface seas. The concept of under-ice drones involves sending a probe to the surface of an icy moon, where it would deploy a melting device or drilling system to penetrate the ice crust. Once through the ice, the drone would navigate the subsurface ocean, equipped with instruments to measure temperature, salinity, pressure, and chemical composition. It would also carry cameras and sensors to search for signs of microbial life or other biosignatures. NASA and other space agencies are actively developing prototypes for such missions. One promising design is the cryobot, a melting probe capable of using heat to tunnel through ice. Once it reaches the ocean, the cryobot could release a smaller, maneuverable AUV designed to map the ocean floor and sample water. These drones would need to operate autonomously, as communication with Earth would be delayed by minutes to hours, depending on the Moon's distance. The problems of designing under-ice drones are enormous. The severe pressure at the bottom of these seas, along with the possibility of excessive salinity or unique chemistry, necessitates the use of strong and adaptable materials. Another challenge is powering the drones, which must operate in the cold and isolated environment using tiny, long-lasting energy sources, such as nuclear batteries or sophisticated fuel cells. By sampling water directly from the ocean, these probes could detect organic molecules, microbial life, or other signs of habitability. They could also study the dynamics of hydrothermal vents, which might serve as energy sources for life. Additionally, mapping the ocean floor could reveal geological features and interactions between the ocean and the rocky core. The deployment of under-ice drones could transform our understanding of alien oceans and the potential for life beyond Earth. Missions to Europa and Enceladus are the most likely candidates for this technology, as both moons have relatively thin ice shells and evidence of subsurface oceans. Under-ice drones represent a bold step forward in astrobiology. Oceanography from afar, detecting alien oceans via spectroscopy. Spectroscopy, the study of light and its interaction with matter, has become one of the most powerful tools for detecting alien oceans. By analyzing the light reflected or emitted from distant planets and moons, scientists can infer the presence of water and other key compounds. This method has already been used to identify water vapor in the atmospheres of exoplanets, and future advancements promise to reveal even more about hidden oceans across the cosmos. When light passes through the atmosphere of a planet or moon, certain wavelengths are absorbed by specific molecules, creating a unique spectral fingerprint. For ocean-bearing worlds, this fingerprint might include water vapor, oxygen, and other indicators of liquid water. Additionally, the reflection of light from an ocean surface could create a glint effect, a phenomenon already observed on Earth from satellites and used to study the oceans of Triton. Detecting oceans via spectroscopy is particularly effective for exoplanets in the habitable zone, where temperatures allow liquid water to exist on the surface. Instruments like the James Webb Space Telescope, JWST, are equipped to analyze the atmospheres of these planets in detail, searching for signs of water vapor and other compounds associated with oceans. For moons within our solar system, spectroscopy can reveal the composition of surface ice and plumes, hinting at the properties of subsurface oceans. When using spectroscopy to find oceans, it can be hard to tell the difference between the signal from the planet or moon and the signal from its parent star. It's especially hard to do this on small, rocky worlds with thin atmospheres, where the signal might be weak. But more advanced methods, like transit spectroscopy, which is when a planet moves in front of its star, help scientists separate parts of the atmosphere with more accuracy. Beyond detecting water, spectroscopy can provide insights into the chemistry and potential habitability of alien oceans. For example, the presence of salts, methane, or organic molecules in a planet's spectrum could indicate unique oceanic environments. Similarly, variations in atmospheric composition, such as seasonal changes in water vapor or carbon dioxide, might suggest interactions between the ocean and the atmosphere, as seen on Earth. As time goes on, more flights will use spectroscopy. Plans for space telescopes like LUVOIR, Large UV/Optical/IR Surveyor, and HABEX, Habitable Exoplanet Observatory, want to take straight pictures of worlds like Earth and study their atmospheres in more depth than ever before. These projects could prove that faraway worlds have oceans and even find biosignatures that point to life, like oxygen or methane. From Europa's buried waters to Titan's methane seas, these extraterrestrial oceans are as fascinating as they are diverse, each holding secrets about the universe's most profound mysteries. What other alien oceans would you like to explore? Let us know in the comments below, and if you enjoyed this journey through the cosmos, leave a like and subscribe to the channel. Thanks for watching, and let's keep exploring together.